Hello, my name is Wei, and I'll be giving this talk tonight, and we'll be talking about artificial intelligence. We'll be discussing this topic, this holy grail of modern times. A week doesn't go by with some headline about artificial intelligence, some massive investment or some breakthrough or whatever. Stephen Hawking, late great Stephen Hawking, said success in creating artificial intelligence will be the biggest event in human history. Wow, that's a big statement, isn't it? And in terms of the commercial end of things, I mean, literally billions and billions of dollars being invested in artificial intelligence. All the big car companies with billion-dollar, multi-billion-dollar investments. World governments getting in on the act now. So Putin said, okay, not necessarily the nicest guy in the world, but he knows a thing about politics. He said, whoever controls artificial intelligence will become the ruler of the world. And the Chinese government last year have stated they're going to be the leader of AI by 2030, and they're putting about $30 billion behind it. And which has made America respond with billions and billions of funding, especially with spending on AI for weaponry and the arms industry. And even the UK government, there is no monetary UK government has allocated $1 billion for AI research over the next few years with help from industry. So this great big event in human history, we seem to be on this verge of this breakthrough. France's Emmanuel Macron, along with France's 1.85 billion investment in AI announced this year, he said, quote, if you want to have a say in the shape of your society, your choice of civilization, then you have to be an acting part of this AI revolution. So literally what they're saying is basically this is going to change the world, alter the course of civilization and society, and the biggest event in human history. So we seem to be on this breakthrough, this transition into some new world of artificial intelligence, with all the kind of breakthroughs that have been announced in the past few years. But when we look at these breakthroughs closely, then we realize something very different. Okay, so behind the hype and behind the headlines and the announcements of the technologists, there's something very different going on, okay, which I'll discuss now. All the breakthroughs are basically, they're not really breakthroughs. They actually involve ideas that have existed for decades, 40, 50 years. So let me explain. Let me go through some examples. Okay, Watson. Okay, it's decades old technology that IBM have had for decades. Okay, so an AI seems to have won the game Jeopardy, but not so impressive when you realize that 99% of all the answers to the questions were the titles of Wikipedia pages. When we realize that Watson was trained on the entire Wikipedia database, then you see it's not so obvious, it's not so impressive, yeah? And so it's old technology, it's not very flexible. It wins in Jeopardy, but it can't play Hangman, a simple word game. Okay, so not so clever. And the recent DeepMind Atari playing AI, now it's very good at the mindless reflex games, absolutely mindless games. But any Atari game that requires even a little bit of thinking, a little bit of look ahead, like Pac Man, then it fails miserably. So it's very good. It's very simple, waggle the joystick corresponding to a certain simple pattern on the screen kind of games, mindless games. And old technology, what's called deep convolutional nets, about 20 years old, based on a technology called backpropagation, which we'll talk about later. That's 40 years old. It's a really old tech. Now, AlphaGo, again, this backpropagation technology with reinforcement learning, coupled with an idea called Monte Carlo tree search, which is actually one of the oldest ideas in computer science. We're talking old, we're talking the first computers running in Los Alamos ran the Monte Carlo algorithm. So this is absolutely textbook stuff, absolutely AI textbook stuff. So hardly a breakthrough, old technology cobbled together to create a game, to win a game, basically, that computers could play already, that at some point computers would have beaten human beings. So they kind of pushed it forward a couple of years. So it's hardly a breakthrough. Again, old technology. So it plays Go, but then it can't play noughts and crosses. So again, narrow, brittle AI. Okay, now as for self-driving cars, okay, so people have been saying that we're going to have fully self-driving cars in a few years. Now that sounds really impressive until you realize what's actually going on. Okay, what's actually happening is these self-driving cars are actually really stupid. They really don't drive very well. Okay, so Waymo, the Google effort in self-driving cars, has driven 8 million miles. Okay, that sounds impressive until you learn that it can't do reliably very well a left turn into a side road with oncoming traffic. Okay, so Americans drive on the right. So, you need signals from the people coming opposite. It's actually quite a complex task to do. It fails. It fails at critical junctures. Basically, it can't do it reliably. It can do it when there's no oncoming traffic or when things are more simple, but it can't do it reliably. And also, it's dawning on people now that basically self-driving car technology is not within the grasp of the existing technology which they're using, which again is this backpropagation deep learning technology, which is 40 years old. So nothing new going on here. And when we see some of the accidents, you realize basically, okay, it drives a car 99% of the time, but it's driving a car in a way that humans don't do. Humans do it completely differently, and it's doing it in a completely dumb way. Okay, the first fatality, basically, it goes right into this lorry. Okay, now it's a white lorry, and it was a sunny day apparently, so it confused the AI, so not very smart. Okay. Okay, this was earlier this year. Okay, that's a car, Tesla, and that's a parked fire engine. I mean, come on, it's big, it's red. Okay, it's parked badly. See, if a human did that, you wouldn't say that person's a bad driver. You said that person's had an epileptic seizure or was neurologically damaged, wouldn't you? You wouldn't say that guy's stupid, because it's beyond stupidity. It's basically not very clever. And okay, that's kind of obvious. That was broad daylight. That was the day before the accident. That's the photograph was taken. So, and the first pedestrian fatality. Now, even the Volvo auto brake system would have stopped for the lady, but the so-called artificial intelligence just plowed right ahead. The sensors were working. Okay, the car was working fine, but the artificial intelligence was not behaving very intelligently. So what's going on? So what's happening? So self-driving cars, this all this impressive seeming technology, it doesn't actually work. Now why? It is because there's a single technology behind all the breakthroughs, and this is something called backpropagation. It's actually 40, 50 years old, this technology. It's behind what's called deep convolutional nets. It's behind what's called long short-term memory. And these are the two driving technologies behind these so-called breakthroughs in your Google Translate also, and also kind of recommendations on Amazon. Okay, so what are the problems with this backpropagation algorithm? Now, we can give a 2-hour talk about the problems, how it doesn't work like human beings. It takes tens, hundreds of thousands of training cycles to learn a concept. One of the leading lights of AI says you don't teach a child a concept of a cup by showing your child a cup 10,000 times. So it learns, but it doesn't learn like humans do. The list goes on and on. Okay, but what we'll address specifically in terms of the failings of this deep backpropagation approach is what's called adversarial examples. Then you probably get a flavor of why these crashes happen, why this technology is very, very limited, and why this technology is not very intelligent. Let me explain. Adversarial examples. Okay, so the backpropagation network identifies that as a panda. Okay, all well and good. Okay, but you can fool the backpropagation network by this is a mask created from this gibbon picture. Now what this mask is basically, what you're doing here is you're altering every pixel in this photo here by a fraction of a percent. Okay, now to produce this picture here, which was identical in your eyes to that picture there. Now the AI thinks now that that's a gibbon. Not very intelligent. Okay, so no human would ever do that. You know that that's basically exactly the same photo. For some reason, it says 90% confident that's a panda. Now it says it's a gibbon. Okay, more of the same. So it can identify these things correctly. Apply this mask where you alter the pixels a fraction of a percent. To you, it seems like the same picture. But now, in all cases, the artificial intelligence thinks these are ostriches. So not very intelligent. And another example of adversarial attack is a 1 pixel. You basically alter 1 pixel, that pixel there, the deer becomes an aeroplane, the dog becomes a cat, the bird becomes a frog. You get the picture. And also you have what's a patch attack. Any object, you put this patch next to any object, and it makes that object into a toaster. And this is what's called a 3D attack. Basically, this is a 3D printed turtle. Now, it looks like an ordinary turtle, but there's a pattern on the shell. It's done in such a way that to fool the neural network, okay, the AI. So all these different views of the turtle, okay, where it's bordered red, in most cases, the artificial intelligence, the neural network, now thinks the turtle is a rifle. So you get the picture. Artificial intelligence, as it is in the world today, this breakthrough technology, so-called, 50, 40 years old, it fundamentally does not work. And this is just not my opinion. This is actually the opinion of the leading experts. The leading light of really one of the top names in AI, the godfather of backpropagation, one of the main people who developed it for 20, 30, 40 years ago. And all the big names were often his students, basically. So 90% of all these big names in AI were his kind of postdoc and graduate students. Now he says, with respect to backpropagation, deep convolutional nets, I think the way we're doing computer vision is just wrong. It works better than anything else at present, but that doesn't mean it's right. My view is to throw it all away and start again. So that is the current situation in AI now. We're heading to what's called a trough of disillusionment. People are waking up, realizing that AI doesn't quite work. Even Tesla, 3 weeks ago, okay, Elon Musk is great. He is Mr. Can-Do. Now, there was an option on the Tesla website for full self-driving capabilities in your Tesla as an upgrade for $5,000 or something. Just 3 weeks ago, they've pulled it off their website because it's dawned on even Elon Musk that his engineers cannot do. Okay, so really, if that's the state of AI. Basically, the optimistic projections, we'll have self-driving cars in a few years. Strong AI is going to be here. Human level intelligence within a few years, kind of thing. It's all kind of receded into the background now. So we're entering the trough of disillusionment. But we won't have another AI winter, because billions and billions. We're talking literally hundreds and hundreds of billions of investment has been earmarked for AI. So there's not going to be some shift of interest away from AI because there's just too much focus, there's too much at stake, too much money involved. So the question now is, what is the next step? How do we proceed to create true AI? So this is what the talk is really about. So this is kind of like the introduction, setting the context of what's happening in AI right now. Now, how do we proceed? We have to consider what's lacking in the quest for artificial intelligence, and what's really lacking is a scientific understanding of the brain and mind in order to create intelligence. We don't even have a definition of intelligence. So how can you create something where you can't even define what you're trying to create? So we need to go right to the heart of the issue and understand what is the nature of human intelligence. Okay, so we're going to go right to the heart of the issue, ask the biggest question of what is the nature of intelligence. And roughly, overall, there's two views. Okay, is intelligence something special, unique, something really waiting to be uncovered, discovered? Is intelligence something fundamental about the universe, something really special that has to be kind of figured out? Or is it some kind of mess, some kind of kludge, nothing special, just cobbled together a bunch of algorithms and you have intelligence? So let me elaborate further by showing two sides of the argument. Okay. Now, versus, it looks like they're going to have a fight, doesn't it? I mean, nice, clean fight, gentlemen, no biting, no hair pulling. Okay. Now, what the right-hand side believe, okay, we'll do them first. They believe that basically there's no special critical algorithm. So to give you a flavor of this debate, this argument, we just go through some of their views, okay, because it's really important. Because it's about what is it to create artificial intelligence. So we're going to answer this question now. Okay. So we're going to go through the right-hand side, who I think are mistaken. They don't believe there's a critical algorithm. Okay. So we'll start with Stephen Wolfram, certified genius. He in his lectures he says again and again, as a young man, I thought there'd be a critical breakthrough that would give rise to artificial intelligence. No, he doesn't think that anymore. Okay, he says that again and again in his lectures. Marvin Minsky actually says, there's no critical algorithm. He said categorically in his lecture, in an interview towards the end of his life, that it was a mistake to look for universal principles in human cognition and the operation of the brain. So he thinks it's all a society of mind, a kind of like a whole bunch of, evolve different societies, kind of algorithms in your brain. It's all kind of bolted together to somehow create intelligence. And the same kind of thinking, Roman Yampolsky and Eliza Yudkowsky, they think basically intelligence is one point in what's called mind design space. Okay, so human intelligence is a point, a tiny subset of a kind of like space of possible minds. Okay, so there's nothing special about it. There's many kinds of minds. So human intelligence is, there's one kind of intelligence that's human intelligence, but many other kinds. So based on this argument, they'll say things like, you don't have to study the human mind to create AI in the same way you don't have to build submarines that swim like fish or planes that fly like birds. That's their argument. Okay, we're going to show why this is false in a minute. Okay, we'll just quickly go through this. Gary Marcus believes that the brain is a kludge. Okay, it's all a random mess. And Doug Lynette kind of spent his career building a kludge called Psych, thinking, you know, all these kind of like simple rules would somehow produce an AI with common sense. Niels Nielsen wrote in his fairly recent book, he wrote he doubts an overarching theory of artificial intelligence will ever emerge, unquote. Ben Goitzel has said there is no critical algorithm for AI and the human brain. And what he believes is basically, now he has said in his writings, that because we haven't found a generative process that can produce all the partial solutions that humans have generated. Therefore, he says that basically the quest to create AI is to cobble together human-generated partial solutions in order to bolt together a kludge that somehow is artificial intelligence. And it's got an integration bottleneck. You can't kind of bring these solutions together. Okay, Danny Hillis says intelligence is not a unitary thing. You get the idea. So basically, this camp says basically nothing special about intelligence. It's all a mess. One kind of intelligence of many. Now, the opposite view is this. Okay, these guys I think are right. Our own Sir Steve Grand, okay, a leading figure in AI in England who basically worked on computer games. Now he said there's a one-sentence solution, a one single formula that you need to create AI. If you have that formula, then you can create AI. If you don't have that formula, you can never create AI. He believes that. And Switzerland's top name in AI, Jürgen Schmidhuber, thinks you can create fully recursively self-modifying, full-blown human-level intelligence with 10 lines of pseudocode. And he thinks there's 5 of those 10 lines already. Okay, Andrew Ng, Jeff Hawkins, Ray Kurzweil, Mr. Tech Singularity, they all believe at least that there's a unified cortical algorithm behind how the brain works, which is most of the brain, 85%. Eric Horvitz of Microsoft has said that there is a deep theory of AI waiting to be found. Jan LeCun has wondered aloud whether there is a single learning algorithm, principle or procedure, unquote, in biological brains. Nick Bostrom of superintelligence fame, who heavily influences Elon Musk, and he has said basically there is a possibility that to create AI, what you need is a small set of constraints that can actually be figured out by a single person. So he has a lone hacker scenario. And David Deutsch, okay, who's an Oxford physicist, works a lot of quantum computers, he says that it's plausible that just a single idea stands between us and the breakthrough that's going to give us AI. Okay, so you get the picture. These people believe there's something waiting to be discovered, something special about intelligence. These people don't. Now, this question is important because it also determines where AI is going to come from. If it is a kludge that's been evolved over billions of years, then it's going to be a massive company like Facebook or some government effort that's going to create AI. But if it is a small set of constraints, a critical algorithm waiting to be discovered, then the lone hacker scenario, it could be a single small group of people or even a single person will come up with AI. Okay, so we're going to basically ask what is the nature of this critical algorithm. Okay, we're saying there is a critical algorithm. Then what is the nature of the critical algorithm? Okay, well, the simple answer is the critical algorithm generates all the other algorithms. So human intelligence is not a point in mind design space. It's the algorithm that searches all possible minds. It searches mind design space. So it's not a case of cobbling together human-generated solutions, partial solutions, in the hope that we create AI. It is critically defined that generative process that generates all the AI algorithms, the separate algorithms. Now, okay, so where do we look for this generative algorithm? And the simple answer is, and this is an old idea, where we look is basically, we basically, this old idea is basically that we use the most creative, prolific, generative algorithm we know of on the planet, possibly arguably the universe. Now, what is that? It's called evolution. All the complexity of life on Earth has been generated with this algorithm. Now, okay, this is a very old idea, and it's a compelling idea. It's compelling, and it keeps returning. It's the idea of MEMS. Richard Dawkins and co. It's the idea of neural Darwinism, Gerald Edelman's neural Darwinism. It's the idea of genetic algorithms and genetic programming. I can go on and on. Ecorhythms, the person who came up with the expression ecosystem, believe that you can extrapolate what's going on in the brain to ecology. So the idea of like what's happening in nature, evolution, is also what's happening in the brain. So we believe that that is the critical algorithm that's necessary for creating AI. But we're going to, in the course of the first part of the talk, we're going to make this, I think, compelling idea into something utterly convincing. Okay, so how am I going to do that? But once you understand that evolution is this critical algorithm, then you realize it's not the case of, building submarines versus fish or building planes versus birds. It's to find that meta solution, that generative algorithm that generates planes, birds, submarines, fish, everything in human culture and everything in the animal kingdom. Okay, so that's the quest. That's the key to creating AI, we believe, and we're gonna show you how we do this in the course of this evening. This is a really ambitious talk, by the way. Okay, so how do we? Okay, so where do we study evolution? Okay, there's this critical algorithm in the brain, and we believe it's to do with evolution. So where do we look? We look in the brain. We look in the genome. But how do we start? I mean, really, there's tons of information about the brain and genomics. These are the biggest questions of the age. How does the brain work and functional genomics? And so where do we begin? But taking off from David Deutsch, what he was saying, okay, that a single idea may stand between us and the breakthrough that's going to give us AI. But then he goes on to say in his essay that it's going to have to be one of the best ideas ever. Okay, well, I can tell you already what that idea is. And I can tell you, we already know it's one of the best ideas ever because it's the key idea behind the entire enterprise of science, the whole notion of universal and unified theories. Now, what is that idea? Okay, the idea is symmetry. Now, symmetry is a really, really powerful idea. Let me explain. Okay, symmetry. Some scientists even say that science is symmetry. That the reason why you're able to have science in the first place is because there's symmetry in the universe. Okay, it's that fundamental. Now, if we're trying to figure out a scientific understanding of the brain in order to create AI, then surely this idea of symmetry must be relevant. Okay, but the trick is, how do you apply the idea of symmetry to understanding the brain? Okay, this is what we're going to explain now. Okay, so this is important for creating AI. Now let me go through symmetry. This was the notion of symmetry that you're taught in high school that emerged during the Renaissance. So let me explain. So you have a square. If you rotate it in certain ways, in 90-degree angles, then it looks the same, doesn't it? It looks the same. It's the same shape. And you have this square. If you reflect it in these axes, it basically stays the same shape. Now, the basic idea is transformation and invariance. So something is transformed. You have a transforming process, but it's invariant. Now, in this case, the shape looks exactly the same. Now, since Renaissance times, the idea of symmetry has been extended. So basically, okay, but the same idea is transformation and invariance. So here we have an original shape. We've basically translated it. We've translated it and scaled it. We've rotated it, reflected it. And here we've translated it and scaled and rotated it. Now, but basically, you see again, we've transformed, but the basic shape stays the same. So transformation and invariance. Now, an important point is the idea that you have transformation and invariance, but it is that an aspect stays invariant. So to extend the idea of symmetry. Now here we have transformation, that literally the shape is changing. Can you see the shape is becoming a different shape? Now the aspect that stays invariant is that it stays the same color. So it's transformation with an aspect staying invariant. But here we have the same shape, but the color changes. The aspect that stays invariant is the shape. Okay, so that's symmetry in a nutshell. when we talk about science, now universal theories, okay, say Newton's laws of motion, okay, a cannonball, you kind of fire it and it kind of makes a kind of parabola shape, okay, and it's basically described by a mathematical equation. Now you take the same equation, you can fire the cannonball somewhere else in the universe, roughly the same, kind of like conditions of the planet. Now the parabola might be stretched, it might be, more gravity, more air resistance, but it's basically the same shape anywhere in the universe. So Newton's laws of motions are universal, invariant, okay? And the notion of unified theories, okay, an example in science, electromagnetic spectrum, electricity, magnetism, and light, they seem like radically different phenomena, but you know for a fact that they transform into one another. So a Prius car, okay, electric car, you charge up the battery, okay, electricity becomes motion through the magnets, through magnetism, becomes light through the headlights, and then when you brake, motion becomes electricity. So they kind of transform into one another. So there's something invariant about light, electricity, and magnetism. You might call it electromagnetic spectrumness. So again, this idea of transformation and invariance. Now, okay, another idea which we use to completely understand the brain is the idea of self-symmetry. It's the notion of self-symmetry or self-similarity, or the notion of fractals. And what this means, basically, we have that same basic shape we had before, but what we do is now we make smaller copies of itself and we nest it within itself. And we do it again, we recursively nest that same shape within itself. We can do it to infinity. Now that shape happens to be a brain, but you see, that's the basic idea of self-symmetry or self-similarity or fractals. That's a kind of natural fractal, that's more of a mathematical fractal, but again, self-symmetry, the entire shape is reflected in bits of the shape. To a classic fractal, which we'll be investigating a lot, is the tree. These are neurons, okay, so like axons and dendrites, and that's a binary tree. So again, self-similarity, each of the branches are like the overall branch. Bonsai is like a great big tree. You take a branch of a tree, it's like a tree, and you even take a leaf, you have that same branching pattern in a leaf. Okay, so to round the point home even more, okay, your classic Russian dolls, and you have these kind of recursively nested, fractalized kind of Russian dolls. And you kind of zoom in on that Russian doll, you have loads of Russian dolls, you kind of zoom in on that one, you take it to infinity, you get the picture, kind of nested symmetry. Okay, so we think these two concepts of symmetry and self-symmetry are the key to completely understanding the brain and the genome and creating artificial intelligence. Now, the trick is to find that aspect which is invariance. So people say, how can you possibly apply the idea of symmetry and self-similarity, self-symmetry to the brain? Because it seems so asymmetrical. How can you possibly do it? That's why people say it's a kludge, it's a complete mess. This is what we're going to show, how we're going to find that invariant aspect. Okay, well, Now we're going to introduce a big idea. We've introduced one of the best ideas ever. We're going to introduce a huge idea. Now, to bring about this Stephen Hawking's biggest event in history, you need a big idea behind it. Okay, so what's that big idea? This big idea also allows us to make the idea of evolution is the same as creativity and human learning. Okay, it makes it utterly convincing. Now, the big idea is basically, that's what we think is the case, that evolution is happening in the brain. So evolution is generating all these algorithms, these AI algorithms, and generating all our behavior and all our learning, all our creativity. So this is what we think, what we've heard so far, this is what we want to show. How do we make it utterly convincing? By putting it into a wider context. Now, the big idea is this: there is a perfect symmetry between life as we understand it and intelligence as we understand it. Now, what's life as we understand it? Life as we understand it is basically, it is evolution. The theory of evolution it is the process of development. Is the genome, gene regulatory networks, and genes. So that's a good kind of like summary of life as we understand it. It covers everything. Now, intelligence as we understand it is basically neurons, neural networks, and brains. And it's also behavior and thought, obviously. It's also creativity and learning. So we're going to show basically that there is a perfect symmetry between a gene and a neuron, gene regulatory network and neuronal network, genome as brain, and perfect symmetry between ontogenesis. So what does a genome do? It calculates a body, ontogenesis, from a fertilized egg. That's ontogenesis. A fertilized egg becomes a body. That's what the genome calculates mainly. That's what it does. Okay. So what does the brain do? It calculates thought and behavior. So we're going to show a perfect symmetry between ontogenesis and thought and behavior. Now this sounds wild. How can it, okay, we'll start. How can a gene possibly be like a neuron? I'll show this first. Okay, and once you see this, everything else kind of like, becomes more apparent. So a gene is like a stretch of DNA, like a rope. Now a neuron is like a tree. Neuron cell body arborizations. The dendrites like the roots of a tree, and axons like the branches of a tree. Now how can a rope possibly be like a tree? I'll explain this because this is important, because it leads to the rest of it. Okay, a gene is like a neuron because, okay, I'm not saying it's analogous to a neuron, it's exactly like a neuron because a gene is basically a coding region. The coding region, okay, so there's multiple splicing as well, but to make things simple, so one gene encodes one protein, just make things simple, okay. Now, this coding region, okay, is activated by what's called an RNA polymerase. So when a gene activates, the RNA polymerase goes down a gene and kind of reads off the RNA. So that's when a gene is activated, okay. So in effect, a gene fires. Now, what's discovered recently, in the past 10, 15, 20 years, that's fairly recent, is the notion of cis regulatory modules which regulate the firing of the gene or the transcription of the RNA by RNA polymerase. Now, you see, this is the loop, the strand of DNA, it's looped onto itself. It actually loops onto the RNA polymerase. So there's a new concept in genomics called the loopome. Genes, the DNA, the strands of DNA are looped in a very precise way. Now, in terms of this gene, there's 3 loops. That's generally the case, 3, 4, 5 outlier cases of 15 loops on a single gene. So data's still coming in. There might be, cases of even more extreme kind of loops. But you're talking like 3, 4, 5 kind of these kind of loops into the RNA polymerase. Now, each cis regulatory module, okay, each of these modules can separately activate the gene. Now, when we examine up here the cis regulatory module, which is about a couple of hundred nucleotides, so it's not a very long stretch of DNA. Now you have what's called transcription factor receptors. So it binds a protein called transcription factor, of which there are about 2,600 in a human body. And okay, so if you get the right combination of transcription factors, then basically the RNA polymerase activates. So effectively the cis regulatory module activates the expression of the gene if the right transcription factors activates it. And what's discovered fairly recently is also these cis regulatory modules do summation. So not just a combination of transcription factors, there's also sum the number of transcription factors and roughly sum the strength of the expression of the gene. Another analogy between genes and neurons, they're both probabilistic. They fire probabilistically. Okay, now, if we have each of these cis regulatory modules, basically what happens is basically they correspond to a dendrite of a neuron. Now, what recent research has shown that basically a neuron, each dendrite works as a separate compartment. So each dendrite is like a disjunction case, like the cis regulatory modules. This dendrite or that dendrite can activate the neuron. Now, if genes do combinatorial processing and summation, okay, it's known for years, and in most spheres, neurons summate the signals coming into the dendrite. But recent research from a few years ago shows that neurons now is been touted as a universal theory of the brain. Basically, neurons code things in powers of 2. So what it means is basically this discovery, literally made 2014, so a few years ago, that neurons behave in a kind of like each dendrite works separately from all the other dendrites. But also neurons summate signals, but also neurons work in a combinatorial manner. Okay, the analogy continues in the same way that basically each of these cis regulatory modules can activate the gene and separate dendrites can activate the neuron. We know that in neurons, each dendrite can be primed separately from all the other dendrites. And in the case of a genome, each cis regulatory module can be primed separately from all the other ones. Literally, in the case of a gene, literally you prime it by having it physically close to the RNA polymerase. And if you have it physically far away, then it's kind of inhibited. But you can do exactly the same thing with neurons and dendrites. Okay, so you see, if this is like a neuron cell body, and these are like dendrites, then the cis regulatory modules correspond exactly with dendrites. Okay, in a kind of simpler way with less inputs, but the principle is essentially the same, summation and combinatorial processing. Okay, and probabilistic firing. Now we've got the dendrites explained. Now what about axons? Okay, so neurons have these kind of point-to-point connections with other neurons. How does that work? Well, if these some genes produce these transcription factors, what it means is basically these are signaling elements that bind onto these transcription factor binding sites on cis-regulatory modules. It means if a neuron fires a certain transcription factor, okay, or bind lock and key style to certain receptors, it means basically when this gene fires, it's like a neuron. Now the analogy is a mobile phone or a landline. Okay, so a neuron is like a mobile phone. You've got a physical wire, an axon, going to another neuron. But you know, if you use a landline or a mobile phone, the effect is the same. It's invariant. You get the message. So what we have is a point-to-point connection with axons and dendrites. But what genes do, there's a transmission medium. You transmit these transcription factors, and they'll go specifically to specific binding sites on these cis-regulatory modules. So effectively, you have this network, point-to-point network, you see. So you can see how genes can be organized into these gene regulatory networks, very precisely wired, like neurons. Okay, I can go on with the analogies of how genes like, but you get the flavor of how basically genes can work like neurons to form gene regulatory networks that are like neuronal networks, to form a concept of a genome as a brain. There's more. In the same way that the brain is hierarchically organized, genes are also hierarchically organized. In the same way the brain has nested recursive kind of Russian doll organization, the same with genes. So exons nested in genes, genes nested in gene batteries, batteries of batteries, etc. Russian doll nesting. And the analogy goes on, okay. But you get the gist of what I'm trying to say, okay, basically of how a neuron is like a gene, of how a gene regulatory network can be like a neuronal network, and how a genome can be like a brain. Now we can give a 2-hour talk about the details of genomics and brains to reinforce this point, but you get the basic flavor of it, don't you? Because just like a time, we didn't move on. We could, okay, to explain the next part, because this is really critical to show the symmetry behind mind and brain. Okay, so okay, how can ontogenesis be like thought and behavior? It sounds totally incongruous. I mean, how? Okay, it's because there's a language, there's a hidden mathematical language behind ontogenesis and all thought and behavior. And I'm going to explain what this hidden mathematical language is. Okay, once you see it, you're not going to look at genes and brains and genomes and ontogenesis in the same way again. And it also gives the key to creating artificial intelligence. Now, this language is the language of binary trees. Now, that's a tree like you see in your garden. That's a binary tree. It just means that binary branches, that can go to infinity. Now, okay, very simple. That's a binary branch. You can represent like this kind of like two squares. You can rotate it. You can that's still a binary tree, isn't it? You see, that's a binary tree. You've got kind of like 2x2 grid. And then you can kind of go with this binary tree language into a 4x4 grid, into etc. Okay. So you can use binary trees to represent 2D spaces. By the way, this is exactly how the latest and greatest video compression technology, H.265, the so-called HEVC, high efficiency video codec, demarcates video frames. Okay, so a bit of geek action going on there. So okay, so it's a very effective language that's actually used in technology. It's on your mobile phone right now. Okay, now we can use binary trees to also represent time. So basically, these kind of little pictures, you can imagine they're like frames of a flick cartoon or kind of frames of a movie reel. And over time, you can basically animate kind of dynamic processes over time. So okay, that is also a binary tree, but can you see it's a binary tree that's called an unbalanced binary tree. So that's balanced, that's unbalanced. Now some computer scientists will say that's a linked list, isn't it? Well, basically it's a linked list, but it's also a binary tree. Now interestingly, more geek action, this binary way of representing lists is exactly how the very first AI language, Lisp, list processing language, how it represents lists. Okay, so it actually represents lists as binary trees. Lisp represents lists as binary trees. So this is kind of theoretically quite satisfying, I think. Now, okay, so more of this language. So you can see that shape here we had earlier is exactly corresponding to this binary tree. It's just drawn in a different way, looking directly down on it. Now this is to show basically that the this shape here, these grids, to show that the language is literally flexible. Okay, so it's a computer language. Can you see it literally flexes around? So this is an animation to show how the trees we had before literally can slide, scale recursively, and also rotate. Okay, it means that the language is literally flexible. We actually encode in the language at the outset this kind of flexible ability to flex around. It's actually literally a flexible language for encoding things. Now, for artificial intelligence, this is very important because it's a non-brittle language. Okay. Now, but is this a mathematical language? Is it a proper mathematical language? Donald Knuth, who's one of the top computer scientists in the world, he has said that binary trees are the biggest contribution that computer science has made to mathematics. But it goes further than that because, okay, this is one of the kind of like interesting facts of the 20th century. One of the most kind of like towering achievements, intellectual achievements of the 20th century, less well known than Einstein's relativity or quantum mechanics. Okay, one of the biggest intellectual achievements of the 20th century was Bertrand Russell and Alfred North Whitehead's Principia Mathematica. So what did they do? Okay, they basically reduced all mathematics, all of it, into set theory. Now what set theory is what's called discrete mathematics. I don't know if you remember, it's in school, they use set theory to teach probability theory, and when I was studying computer science, used that to teach Boolean algebra and logic. So it's called discrete mathematics, and basically it's all interrelated: set theory, Boolean algebra, probability theory, logic, etc. Now the important thing here is that all the structures of Boolean algebra and logic are binary trees. All those nested parentheses of Boolean algebra, logic, and also Lisp is basically representing binary trees in a linear format. All the relations of set theory and probability theory and etc. Boolean algebra are binary. Okay, so what it means is basically we merge the power of discrete mathematics, to which all mathematics reduces to, with our spatialized, twisty, turny, temporal trees that represent space and time. Okay, that does Lisp and does H.265 video compression. So this is the really powerful language that we're going to now use to show that this language is completely the hidden symmetry behind mind and brain. Okay, so we're going to now go wade through loads and loads of neuroscience data to make this point. Okay, but we're going to be like a skimming stone. Obviously, there's tons of knowledge about neuroscience and genomics, but and developmental biology. Like a skimming stone, we're going to skim over and show that this pattern is absolutely ubiquitous. Okay, absolutely, and I mean it, absolutely everywhere. Okay, so let's begin with this thing called hemi-neglect. It's to do with what's called egocentric mapping. It's how you map space. Now, sometimes we learn how things work when they go wrong. This is a case in point. What happens in hemi-neglect is you lose half your world. Okay, so a man with hemi-neglect or a woman with hemi-neglect asked to imagine walking down the street where you live. Okay, that lady can walk down the street and recall everything on one side of the street, but not the other side. But tell the lady to walk to the end of the street and turn around, then suddenly she can recall everything on that side of the street now. Okay, and asked to draw a house, the lady or guy draws half a house, kind of loses half a world, half a flower. Goes into a restaurant, reads a menu, and he sees half the words. Eats a plate of food, okay, starts eating, then stops eating. Then you turn the plate round and she starts eating again. So you see, it's a kind of binary divisioning to how we represent egocentric space. Now, okay, this is my daughter. Okay, I don't know if you can see those little hexagons. Okay, this is the hexagonal grid on the floor, okay, to represent the Nobel Prize winning work of 2014. Moser and Moser won the Nobel Prize for what's called grid cells. It means that as I walk around, or my daughter cycles around this space, okay, neurons in her part of the brain called entorhinal cortex will light up when she's in the middle of these hexagons. It's like the brain projects a hexagonal grid on the floor as you move around. If you go to the center of this hexagon, you kind of project on the floor, then the neuron fires maximally. Okay. Now these hexagonal grids come in certain sizes, specific sizes. Now, the important thing is the scaling factor of these different size grids is 1.42. Now the relevance of that, 1.42 is the square root of 2, which means you times it by again and again, you double, okay, or you halve it, you halve it if you go the other way around. So again, it's doubling phenomena with respect to grid cells, the Nobel Prize winning work. Okay, spatial frequency, your eyes process pictures in terms of spatial frequency. What does it mean? Okay, that's a frequency curve as you see it. But can you see underneath, there's what's called spatial frequency. It's basically over space, that curve is kind of corresponding to these kind of like changes in contrast underneath. Now, experiments done about 20 years ago shows a paradigm called just noticeable difference, that you can tire out the spatial frequency processing elements in your brain in terms of octave subbands, which means that basically the just noticeable difference goes up. So you have to increase the contrast, but this only happens within 1 octave. You go 1 octave above, 1 octave down, then there's no effect. So again, halving, doubling in frequency. Now, okay, so basically this is halving and doubling in frequency. It just means you can draw a binary tree straight through it to create what's called a wavelet. So the correspondence between, doubling frequencies and binary trees. Now, brainwaves, again, if you look at an EEG, there's lots of spectral spread. It's kind of messy. But when we look under the surface of the skull, then the brainwaves come in very specific powers, very specific frequency ranges. And this is the idea that all the brainwaves are harmonically nested. Now, in music, the most harmonic interval is the octave. Now, what we find, basically, this is exactly what we find. The main brain waves, 40 hertz gamma waves, 20 hertz beta waves, are in powers of 2. 10 hertz alpha waves, roughly 5 to 6 hertz theta waves. And, okay, with respect to language, okay, work of Noam Chomsky and a lot of other people, you can decompose all human language in terms of binary trees. So, okay, obviously that's a binary tree. Brains think, that's a binary tree. Then you double that, fractal brains think binary. They can nest that binary tree in a bigger binary tree. Way thinks, fractal brains think binary. You can analyze all human language in those terms. Now, what was suspected for a very long time was confirmed literally 4 or 5 years ago in actually a lab in Scotland, a lab in France. It's the idea that basically phonemes, okay, spoken language, okay, phonemes are processed using gamma waves and syllables are processed using the theta waves. So this is confirmed finally. It means there is a doubling processing hierarchy for language from the syntactic level right down to the phoneme level. Okay, we'll go on. I mean, music, okay. Common time classical music, pop music, rock music, folk music, limericks, nursery rhymes. There's a certain grouping of the beats. 4 beats grouped into 8, grouped into 16, grouped into 32. Okay, so it's kind of doubling boxy structure to the kind of music that is popular, that's accessible. So the simple idea here is basically that is because it's how the brain processes information. Okay, and we'll go on. Okay, so we've gone from cognitive science, spatial mapping, vision, everything, language, thought, to now developmental biology. Now, mitosis obviously is a binary process. Fertilized egg goes into 2, 4, 16 cells to make all the 15, 20 trillion cells in your body. Okay, that's a binary branching process. Now, what's also binary is that the idea that progenitor fields, which is groups of millions or even billions of cells, progenitor fields also bifurcate. Okay, so basically the notion is a very old idea that basically this is a progenitor field, and then when the progenitor field has to split into 2 fields, it's a bifurcation. There's a very specific machinery that does it. It leads to the idea attributed to people like Brian Godwin, one leading developmental biologist, that all biological development is a bifurcation diagram. Okay, so basically your body, development of all biological organisms from the level of cells, mitosis, and the development of progenitor fields is a binary bifurcating process. Now, people sometimes talk about trifurcations. Yes, there are trifurcations in the lungs, in the kidneys. It doesn't, but it's very unstable. So one of the kind of leading lights of a field called mathematical biology, James D. Murray, who's written kind of 2 telephone directories, 2 volume set called Computational Mathematical Biology, states explicitly that's very hard to get a trifurcation going stably, reliably. Okay, So it doesn't matter whether some of your branches in your lungs and your kidneys are trifurcating, because that's statistical. It's basically noisy, and sometimes it will trifurcate and bifurcate. But it does matter whether you have 3 legs or 2 legs. So if you want to reliably reproduce a certain pattern in ontogenesis, then basically what's happening is bifurcation and doubling, binary processes. We can go on. Okay, the Nobel Prize winning work of, okay, this is a fruit fly embryo. Now the gene has to have an idea of space, because a gene has to allocate arms and legs in the right place, doesn't it? So basically the genome has to basically calculate from a fertilized egg, a body. So it has to have some notion of space. Now how it does it in the fruit fly, Drosophila, there's a recursive binary subdivisioning process using chemical markers. So this is over time. Basically, the key idea is basically it's a binary doubling process. And with this, these chemical markers, you can accurately form a grid on the long axis of a fruit fly in which you can allocate transcription factors to activate formation of arms, legs, antenna, etc. in the right places. But again, this doubling pattern. Now, okay, the formation of arms and hands, and basically there's a basic program in all vertebrates, and also from fish. There's a basic algorithm. Basically, you take what's called a condensation. It's also a progenitor field, really. And you can basically run this algorithm recursively. So basically, you can branch it as a binary fork. And then you can break a bit off. That's a binary process, breaking a bit off. If you recursively apply these steps, you basically form 1 bone, 2 bone, many bones, digits. So that's the basic pattern from primitive fish to all vertebrates. 1 bone, 2 bones, many bones, digits. And from that, you can create fish fins. With a bit of scaling, that same basic program allows you to create a human arm and hand, a cat a kind of leg and paw, a bat's wing, and a whale flipper. But the basic program is binary. So you see, we've gone through oodles and oodles of developmental biology to show that this binary pattern is ubiquitous. But this is the aspect that stays invariant with respect to learning, behavior, and ontogenesis. But we can go on to apply this binary language to then encode genes. So what's a gene? It's a rope, but it's like a linked list. So we use this binary tree language to encode genes. But also neurons are literally binary trees. The axons and dendrites are always binary branching. We can in fact use this binary language to encode the entire diagram, the bottom part of the entire diagram. So this is the aspect that stays invariant. This is the hidden symmetry, which allows us to basically see everything in this diagram as one thing. Now, okay, evolution and learning creativity, this is what we want to kind of show is the case. Now, okay, Anthony Brandt and David Eagleman. David Eagleman's one of the world's top neuroscientists. Okay, he recently had a TV show, I think I showed on the BBC or Channel 4 or whatever. Okay, so one of the top neuroscientists. Now they've written a book, David Eagleman and Anthony Brandt, called Runaway Species. Basically, it's about human creativity. To summarize the entire book, what they say is basically, it's not a new idea, but it's roughly in the right ballpark. And it's basically an old idea that's been nicely communicated. They say that human creativity is basically taking existing ideas. And what you do is you do 3 things. You blend, you break, and you bend. So all human creativity is taking existing ideas, break, blend, and bend. Now, all those 3 transformations you can do to the world of genomics and ontogenesis. So blending, okay, my ex-partner is, she has brown hair, and I have black hair. So my kids, they have dark brown hair. Blending. And my older daughter has slightly darker hair than my younger daughter, so variation, blending and variation. Now, okay, so bending, okay, this is exactly what we've had here. This is bending, okay, this is ontogenesis. And also, Galapagos Island, Darwin's famous finch's beaks, kind of bent and stretched and extended. Okay, so that's another example of bending. Now, breaking is essentially what you do. You can break genes apart. You can mix them and match them, crossing over. So you can break genes apart, and you can break them apart and then slog them together again. Okay, so all the transformations of human creativity you can do to the world of genomics and ontogenesis. Vice versa, all the transformations of evolution. Okay, what's been known for a long time, point mutation and gene insertions and deletions. Okay, so simple, human creativity. Okay, I change a word in a poem, or I flip a letter in a bit of prose, or jazz, or I played a note wrong, but the music sounds better. Okay, so you see, it's like a point mutation. You should flip one little bit, and basically you've got a better song or a better poem. Change a word, change a note. Okay, now point mutation, crossing over. You can basically kind of splice ideas together and kind of blend them and kind of like change them in that way. Now, a mechanism called retrotransposition, which is basically believed to be the main mechanism behind most primate evolution that's gone on recently. Okay, half of your genome is made up of what's called retrotransposable elements. Let me explain what retrotransposition is. Okay, retrotransposition is basically you take a bit of a section of gene. The retrotransposable element, what it can do is it can copy and paste. So it can copy itself and paste itself to another section of the genome. Now, transposons, jumping genes, are like cut and paste. You cut out the gene, then it literally cuts itself out, then it transposes itself. That's been known for a long time. Retrotransposons, copy and paste. And it's believed that this is one of the main driving forces of evolution in terms of primate evolution and human evolution. And in terms of human creativity, human creativity has become often copy and paste with break and blend. So, the idea that lesser artists borrow and great artists steal. And, a lot of computer technology, literally creativity, human creativity is literally copy and paste. Okay. The main point is that all the transformations of human creativity apply to the realm of genomics. And all the transformations of genomics can flip over and apply to the realm of human creativity. So basically, the transformations are completely interchangeable. But once we understand that these transformations of evolution and creativity basically work on the same structures that are identical, these binary tree structures that are ubiquitous throughout the brain and also the genome, ontogenesis, thought and behavior, that is actually based on a substrate, given our way of looking at things, that is completely symmetrical. Gene as neuron, gene regulatory network as neuronal network, genome as brain. What it means is that there is a perfect symmetry between life as we know it and intelligence as we know it. Okay, so basically this is a big idea, which leads to an even bigger idea of we can use this idea to explain what is the nature of life and intelligence in order to define what is life and intelligence to create artificial intelligence. And this is what we'll do in the next part of the talk. Okay, what we're going to do basically is this. You can see there's a symmetry going across in terms of invariance. Okay, we're not talking metaphor, we're not talking analogy, we're talking symmetry. The next part of the talk will show there's a symmetry going all the way down, all these elements that unifies everything in this diagram into a single algorithm and single concept. And the key behind this algorithm is what's called recursive self-modification. Okay, let's continue the rest of the talk. Now, basically, this is the main part of the talk. The first part is introductory. We introduce some big ideas, but this is the kind of punchline, really. So, okay, this is put things in context. Okay, so basically, we need a revolution in science to understand the brain. So basically, we need to explain what science is quickly to explain the next part of what we need to do to understand the brain and genome, create artificial intelligence scientifically. Okay, in a nutshell, okay, very quickly. Okay, Kepler, Brahe, okay, joining the dots. Science is joining the dots. So literally, Tycho Brahe had the dots, observational data of motion of the planets. And Kepler's job was to join the dots. His big innovation was elliptical orbits. Okay, so elliptical orbits around the sun. Okay, so obvious now, but it was a big breakthrough back then. Okay, along came René Descartes. Now he can describe ellipses using algebra. Okay, he kind of extended the work of actually Muslim thinkers. And then along came Isaac Newton and Gottfried von Leibniz, who then invented differential calculus. Now you can see how the dots change in time, the dynamic of how the dots change. So in a nutshell, that's how science has been done in the past 300-400 years. The dots have become more complex. The algebra, the calculus is far more complex and convoluted, but that's the same basic idea. Okay, or instead of joining the dots, statistical science, you're corralling the dots. So the same basic idea throughout. So we've got the language already. We have the language in terms of this set theory, binary tree mathematical language to join the dots and see the hidden symmetry. we're going to explain what's the overall pattern that unifies this diagram. Now, it's kind of obvious that a gene, okay, produces ontogenesis, and that we're here, that's a given. Evolution has produced us, everyone in this room. Okay, but once you have ontogenesis, then basically ontogenesis, the one cell, gives rise to all neurons, the neural network, the brain, thought and behavior. And you can do learning and creativity because from a fertilized egg, basically that became a body and brain, and your life emanated from that. Now this is a really fundamental idea. Look, it's kind of completely obvious. Everything in your life, absolutely everything in your life has emanated from a fertilized egg. Without that point of fertilization, nothing, absolutely nothing would have happened. That's obvious, isn't it? Okay, so from that point of fertilization, absolutely everything that's happened in your life, every protein that's been manufactured, every spasmodic movement, random nerve firing, every inspired thought, purposeful action, regrettable action has emanated from that point. Now what we're going to propose is that, okay, that's obvious. There's a single chain of causality from fertilized egg to everything in your life. We're going to propose there's a single algorithm, there's a single mathematical process which captures everything from a fertilized egg. So there's a single underlying symmetry of a dynamic process that captures everything from a fertilized egg. That is a single algorithm, and that's what we program to create artificial intelligence. Okay, this is a bigger idea. Okay, what is that symmetry? Okay, so basically, like the branches and leaves of a tree branching out and the roots of a tree, basically that fertilized egg becomes everything in your life. Everything in your life has emanated from that point. Okay, what is the fundamental algorithm that basically gives rise from a fertilized egg to your entire everything in your life? It's a branching, emanating process. And we've got all these binary trees describing everything in this diagram. But what is that fundamental algorithm? I'll tell you what the algorithm is. Okay. Now the folks at the Santa Fe Institute who study what's called complexity science, okay, basically when they describe evolution as an algorithm, they say it's three things. And it's a very succinct and correct description. They say it's differentiate, select, amplify. In recursively differentiate, select, amplify. What it means is basically differentiate. It means kind of descent with variation in Darwin's own words. It's basically the production of variation. So that's basically differentiate. Basically, descent into different species and variation between members of the same species. So differentiate. Now you select, obviously natural selection. You select certain species, certain individuals get to breed and they become, express more in a gene pool. So basically that's, you select and then you amplify. So basically those genes, those people become amplified in the population. So basically evolution, or the species become strong, the species spreads out and becomes multitudinous, etc. So evolution is this process of differentiate, select, amplify, applied again and again, generation after generation. That's the basic algorithm. Okay, and it's essentially correct. Yeah, such interesting questions. I forgot to take a drink in the break. Okay, now ontogenesis is also differentiate, select, amplify, because from a fertilized egg you differentiate into different cells and different progenitor fields, but now you select certain progenitor fields to be strengthened. And there's what's called programmed cell death, apoptosis, and certain progenitor fields are programmed to die. You select certain ones to amplify, certain ones to wilt away. And also the formation of certain cells like neurons. Okay, differentiate into different neurons, but the neurons compete. They compete for neural growth factor. The ones that win get neural growth factor, get the blood vessels, they become big and strong. The ones that don't, they die. So ontogenesis from the cell level and progenitor fields, you differentiate, you select, and you amplify. Now, okay, axons and dendrites. How do neurons actually work? We want to basically replace existing neural networks that don't work very well, as we showed earlier. But how do neurons actually work? Okay, real neurons, they are constantly in a state of flux. They're constantly moving around. The axons are constantly branching, every second. They're constantly shifting around, exploring, branching. Dendrites constantly shifting. It's constantly in a state of flux. But then what is the neuron doing? Basically, it's literally a tree structure. The branches are differentiating into space. And by certain criteria, certain branchings are selected. And what's selected is basically when an axon intersects the dendrites. And there's a correlation between presynaptic, postsynaptic, find what's called STDP, spike time dependent plasticity. Certain of those branchings are selected to be amplified, literally amplified, long-term potentiation, literally the synapse is strengthened and some synapses are depotentiated. And most of these kind of like transient bonds, they wilt away, like species that disappear, or people who don't breed and don't pass their genes. But again, the idea is basically what neurons are doing, they're differentiating, selecting and amplifying physically into space with other neurons. Okay, learning and behavior. Okay, so basically behavior and thought. Okay, so basically we've got to go into this in a bit more detail because it relates to reinforcement learning. So this is what DeepMind does, reinforcement learning in artificial intelligence. Okay, and basically we need to explain this a bit further to explain what is thought and behavior and what is reinforcement learning. Okay, so it's a bit of neuroscience now. Okay, so okay, that's my brain from a scan years ago. Okay, not very impressive, I mean, but okay, basically that's me, that's my brain, and every brain is basically composed of 2 flat sheets, and that's drawn to scale. Can you see that's a flattened out cerebral cortex? So literally on each side of your head you have both massive flat sheets scrunched up. That's why we have this kind of convoluted folding kind of appearance, and it's pretty big. I mean, it's now this is the same flat sheet, but it's been demarcated into what's called Broman areas. There are about 50. Modern research, that's done 100 years ago, modern research has demarcated further about 500 different areas, little patches like a patchwork quilt. And different areas do different things. That's a primary visual cortex, that's involved in the higher thinking, that's your primary motor cortex, etc. So basically little patches of cortex do different things and represent different things. Okay, for the purpose of explaining things, we don't have to go into too fine detail. Okay, so that's kind of the same areas in a folded up kind of brain. The frontal lobes is to do with thought and behavior. These are your primary, secondary motor cortices and supplementary motor areas. This is parts. Visual areas. You get the picture, yeah? Now, okay. Now, all the parts involved with doing things. Okay, I think, or I recall a memory, or I move my arms and hands about, or I think complex thoughts in my head. These are actions which I do. All the parts of the brain involved with doing things, active behavior, internal or external, work with a part of the brain called the striatum. Okay, that's the striatum. Okay, drawn within your brain. Now, the striatum, different areas of striatum have a correspondence with different areas of the cortex. So the patchwork quilt, each area of patchwork quilt has its own little patchwork blob on the striatum. Now, what happens is that each area of cortex forms a closed loop with its area of striatum. So this diagram represents primary motor cortex, secondary motor cortex, and supplementary motor areas. You see, that's cerebral cortex. This is the striatum. This is the closed loop. It kind of loops around. Now, all behavior is basically successions of frames of patterns of activity over the cerebral cortex, and it's discrete. It's discretized. It's discretized to the gamma wave. So basically, things presented at the trough of a gamma wave, you don't register it. So things like the kind of sniffing of a rabbit, or the kind of like whiskers of a mouse, they scan at about 5-6 hertz, the theta frequency range. When you scan your eyes around a room, it's actually 10 hertz. The information corresponds with the peaks of the alpha waves and the theta waves. And when information is presented at the troughs, it doesn't get registered. So basically, your processing of information is chopped up, it's discretized, like the phonemes and syllables we saw earlier on. Okay, that's an important point. Now, the important point is basically that all behavior and thought can be represented as successions of states over the cerebral cortex that are animated by this loop with the striatum. Now, the striatum is modulated by a chemical called dopamine. Okay, so this is how reinforcement learning works. Okay, one of the most famous dopamine pathways is the ventral tegmental area. All addictive drugs activate the ventral tegmental area, striatal area corresponding to the cerebral cortex, the frontal lobes. So basically dopamine is a really important chemical. If the dopamine doesn't flow, then the frontal lobes don't work, the striatum doesn't work. Parkinson's disease destroys dopamine neurons. You can't move. and later on you can't think. Okay, so what does dopamine do? Okay, so how it works is this. Okay, so what's reinforcement learning? Okay, basically, if all behavior is the expression of these loops animating successions of patterns over your frontal cortex, different patches of the patchwork quilt, then reinforcement learning is the reinforcement of certain patterns that lead to reward. Okay, so if you imagine, basically, you can imagine that behavior is this kind of random search into a space of possibilities. Okay, so basically, if you the criteria for the dopamine neurons reinforcing this kind of loop to bind two behaviors together in time. Okay, basically the criteria is unexpected reward. Okay, so and the criteria for weakening the link is disappointment. Okay, so I'll give an example of an unexpected reward. Okay, so I'm basically walking down the street and I suddenly have an orgasm. No, bad example, bad example. Okay, not very realistic. That's not very, okay, I'm walking down the street and I suddenly see a £10 note. Okay, unexpected £10 note. Okay, that's an unexpected reward. And basically, what happens is then, wow, £10 note, dopamine flows. What happens is the behavior leading to the £10 notes, okay, basically gets reinforced. Literally, the dopamine binds the succession of states that leads to that £10 note. Now, if I see that £10 note a few times and I get really excited, I get the £10 note. But suddenly, if I expect it, then the dopamine doesn't flow anymore. There's no longer that reward. It's become a learned behavior. Now, if I'm walking down the street now, okay, basically, I kind of expect my £10 note. Then I don't see it. Then the dopamine levels drop. And what happens then is basically this long-term depression, the link between two successive frames of behavior in a chain leading to walking down that street to see the disappointing result of no £10 note, those links get weakened. Now, if you imagine life as a random walk through different things we explore, walking down that street, trying out that restaurant, meeting that person, it is a succession of sudden surprise pleasures and also disappointments. But that essentially is reinforcement learning. So basically it is, but the important point is basically this process, we use walking down the street because literally we can visualize it. That process is a case of differentiating in all the different streets you can walk down. The streets where you don't receive a £10 note, the streets where you do receive a £10 note. Okay, that's differentiating into a space of possibilities. You select certain paths where you get the £10 note and you amplify those paths literally with dopamine. The main point, you can extrapolate this idea of succession of brain states over cerebral cortex, looped with these striatal loops reinforced with dopamine to any behavior and any thought. But the main thing is the algorithm is differentiate into different behaviors, selecting certain ones that get rewarded to amplify. You get it? So basically, differentiate, select, amplify is also happening at a level of complex thoughts and behavior. And it's a universal thing because the underlying circuitry is identical for the entire, every modality of doing you can think about. Now, okay, this leads to, just quickly go over this diagram. Now, basically, this is just to show how a recursive loop is really a binary tree. It just means that, okay, so basically this is a neuron or cortical patch. It just means that it receives a signal at time t. At time t plus 1, the signal from time t loops back on itself, and what you're processing is t conjoined with t plus 1. So what dopamine is doing, it's basically solidifying this link between t and t plus 1, and it's doing it recursively. So that's basically our unbalanced binary tree, how Lisp represents lists from earlier, but reinforces dopamine. Okay, this earlier diagram leads to this hideous diagram, which is a diagram of the entire organization of the entire brain hierarchy. Now, this part here, the stratum with respect to primary motor areas, is this part of the diagram here. Dopamine neurons, what's called a putamen, and the primary motor areas, primary, secondary, supplementary motor areas. These are the cognitive areas, and the symmetry extends to the emotion centers. So basically, the same stereotypical pattern of connection is represented throughout the brain. Now, I include this diagram because basically it's application of the idea of symmetry to understanding the entire brain. So the emotion centers look nothing like the centers of thinking and look very different from the centers involved with kind of moving arms and legs about, the primary motor areas. But the diagram basically emphasizes the symmetry underlying the entire brain. When you want to create AI with a method called whole brain emulation, this way of applying symmetry to the entire brain makes the problem far more tractable. So literally reverse engineering the brain, the dopamine systems, the striatal areas, based on actual physiology and brain anatomy. So I just stuck that in for the people interested in whole brain emulation. Okay, so basically you can see there's a symmetry between differentiate, select, amplify, evolution, ontogenesis, how neurons actually work, thought and behavior. And because there's a symmetry between evolution and learning and creativity, then basically, once we have behaviors and thoughts, then we basically evolve those behaviors and thoughts using exactly the differentiate, select, amplify algorithm. It means that everything in this diagram is basically the same algorithm. Differentiate, select, amplify. Now, if there's a forward diverging into space, okay, there's a backward converging. Okay, let me explain this. There's a backward. This is necessary to unify artificial intelligence, which we're going to do next. Okay, the backward converging is really important because basically it's to do with meaning and purpose. Okay. This is called a diffusion limited aggregate. It's used to study phenomena like the formation of snowflakes in cities. It's basically natural growth phenomena. Now, basic idea, you start off with one single point or 4 points, and basically you have what's called a random walk of points, particles. Now, can you see this is an animation, kind of. Now, when I click it, basically, can you see it's growing? So what it is, there's loads of these little black specks, and they're basically random walking. They're basically drifting around. Now, when a black speck bumps onto an existing like sticky branch, then it grows the diffusion limited aggregate. Now, this starts from actually 4 pixels. It starts from a blue pixel, a kind of red one, a green one, and a kind of purple one. Can you see what's happening? Basically, when we start the program, we start it again. Basically, it okay, we start it again. It starts from 4 pixels and it grows outwards. It grows backwards. Now, basically, this is a model for how we form meaning and purpose in our lives, because what we have when we're born is basically what's called unconditioned reinforcers. We don't know anything about the world. We don't know what's rewarding. We have a basic sense of hunger, how to satisfy hunger first, basic things like desire for sugar, fats, etc. Basic things, basic kind of rewards. But what we do is we backward chain. This is what the expression psychologists use. We backward chain from primary unconditioned reinforcers that are hardwired in our genes, and we backward chain a chain of meaning from that. So as a baby, we know nothing about the world, but we kind of backward chained the notion that we're hungry. Okay, something went in our mouth, and then we were not hungry. Then we backward chained that what went into our mouths came from a jar of baby food. Okay, just contriving an example. And that baby food comes from the cupboard, and then we backward chained that baby food came from the supermarket. Then we backward chained that we need money to buy the baby food. Then we backward chained. You see, from the basic unconditioned reinforcers, we form a web of meaning of everything that's meaningful in our lives. Okay, so the blue color demarcation might be food. The green one might be like sex or football. I mean, depending on your priorities. I mean, the red one might be kind of like, some other primary drive like warmth, etc. But what I'm saying is basically based on these primary reinforcers, you construct your entire web of meaning and purpose from a baby. But the idea is that you backward chain. Okay, backward chain. This is actually an accurate model of how we actually learn meaning and purpose. Okay, so the idea is basically the forward chain of reinforcement learning kind of forward branches into the backward chain, and the two intersect. So basically you form your kind of, when I walked across that £10 note, that was learned, that was backward chain from primary reinforcers. So when I basically walk down the street and I see a £10 note, I go, wow, yeah, £10 note. See, the forward chain of all the things I could do, the streets I can walk down, has backward intersected with the backward chain. So that's the kind of overall structure of how we can represent our entire lives as a single emanation and a single aggregation. Because if that is this diagram represents the entire web of meaning of our lives, there is a central prime directive. Okay, I want to say something really obvious. Okay, it's not. It's kind of profound, but it's completely obvious. We start from a fertilized egg. Okay, everything as we've kind of explained, differentiate, select, amplify. The single algorithm creates everything in our lives. But as a prime directive, if this is our entire web of meaning, there's a prime directive, and it's called the process of fertilizing eggs. So that's the overall kind of like, the kind of elliptical orbit to understand our entire lives. Basically, a single emanation from a point, a fertilized egg, to the prime directive of getting ourselves in a good position to fertilize eggs. Okay, so is that your killer punchline? Is that your big idea? No, that's kind of stating the obvious. I'm just saying that basically there's a way of looking at our lives, which is a single concept like the elliptical orbit, that can be described in a single overarching concept that's completely kind of symmetrical. So we can go on. I mean, this idea of a tree branching, looping back, this same idea applies to neurons. So every neuron pyramidal cell has a flowing inwards, flowing out, branching back columns, organizational structure in the cerebral cortex, flowing in, flowing out, like a tree, patches of cerebral cortex flowing in, flowing out, branching back. So the basic pattern is repeated like Russian dolls. So the basic pattern relates to complex behavior and is backward chain of meaning and purpose. Then the basic pattern is also represented at a neuronal level, cortical level, pyramidal level, and cortical column level. So completely fractal, right down to the genetic level, genes and gene regulatory networks. Okay, so artificial intelligence. Now we're going to basically explain how everything we've talked about completely unifies existing artificial intelligence and how it solves the biggest problem in artificial intelligence. Okay, so this is really the main, what is a series of conclusions. This is the first one. How do you unify existing artificial intelligence? Now, okay, what all existing artificial intelligence? Now how do I summarize what is all existing artificial intelligence? Well, okay, two books. Now this is the book on artificial intelligence. It's called Artificial Intelligence: A Modern Approach. It's written by Peter Norvig, who's the head honcho of technology at Google Corporation. Okay, Stanford professor, actually taught the founders of Google, Larry Page and Sergey Brin. So he's actually the overall head of all technology in Google. And along with Stuart Russell, they wrote the book on existing artificial intelligence, used by 95% of all English-speaking courses, undergraduate, postgraduate, postdoc courses in artificial intelligence. So it is the book about artificial intelligence. The Master Algorithm was a book that came out a few years ago. Now, the Master Algorithms supposes to unify all machine learning, written by a professor of machine learning, Pedro Domingos. Recommended by Bill Gates, king of the nerds. So he really has made the rounds. I mean, I don't mean it's an offensive term. I mean, I spend loads of time in front of the computer reading books, and if I don't wear glasses, but if I broke them, to fix them with a bit of tape and wear them anyway. It's exactly the kind of thing I'd do. So I don't mean nerd in a derogatory way. I mean in a kind of general, I am a nerd, okay. Okay, look, that's a bit of a diversion. Okay, look, Master Algorithm. Okay, Master Algorithm is a good survey of all machine learning. Now, these two books taken together is a good survey of all artificial intelligence, machine learning. Okay, now we're going to unify all the main ideas. Not every single idea, because not all the ideas in these two books are good, but the main ideas, okay, the so-called 5 or 6 tribes of machine learning, and the central idea in the artificial intelligence main book that's used on the planet. This is the main textbook, basically. Now, there's a fundamental idea in this book, Artificial Intelligence: Modern Approach. It's a fundamental idea, and I call it the most fundamental idea in AI because, okay, the first 10 chapters, apart from the first 1 or 2 chapters, about 8, 9 chapters repeats this idea again and again, the first chapters. So it's really a fundamental idea. Now, this idea basically, this core idea in artificial intelligence, which is probably the most fundamental, it is the most fundamental idea in existing artificial intelligence, is this notion, okay, this is a diagram from the book, a schematic view of bidirectional search. So the first chapter is about search into a space of possibilities. So what they say is you can forward chain search into a space of possibilities, then you backward chain from the goal state. That's the overall idea. And with respect to gameplay, okay, basically you forward chain from, okay, a chessboard position, say, or a game state. You forward chain into all the moves you can make. Then you backward chain into the goal states, which is checkmate. I want to win, you know, all the end games. The idea comes again and again. So you talk about forward chaining logical expressions and backward chaining from the logical expression you're trying to prove. Then in the chapter on situational calculus and robot control, you're expressing robot positions in terms of predicate calculus, logic, essentially another kind of logic. You forward chain situations the robot can be in, and you backward chain where you want the robot to be. But can you see it's the same basic idea in terms of game states, in terms of search states, in terms of logic states. It's the same fundamental idea. But the same idea here is exactly what we've been talking about. It is our diverge into a space of possibilities, differentiate, select, amplify. And this kind of backward chaining and the convergence of the two. What I'm saying is that this most fundamental idea in artificial intelligence is exactly the symmetry of process we are talking about, but we're taking it to the max because we're showing that it's completely symmetrical and it applies completely throughout the brain. We're also making it completely fractal, recursively nested. So that's an innovation. Okay. So really taking this idea, putting this idea into we're unifying it for one. We're unifying all these kind of early chapters of this main textbook. And we're also kind of basically taking it, putting it on steroids, basically. Okay, so that's a really important idea, which basically converges with what we've been talking about. Now, okay, so master algorithm attempts to unify the so-called five, well, he kind of marks out 5 tribes. There's really 6. And this covers, he believes, and it's a good survey of all machine learning. So I'll cover what these 5-6 tribes are. Okay, so basically the first tribe, evolutionists. So basically this is what we've been talking about, evolution. Okay, so now Pedro Domingos explicitly writes in page 140, he says explicitly, okay, ontogenesis. Ontogenesis is really important in development, but there's no analog in machine learning. Then he says, quote, we may be missing something important there. Well, absolutely, because ontogenesis, you don't understand evolution without understanding ontogenesis, because ontogenesis has this binary structure. And also this whole, Evo-Devo, this study in developmental biology, basically you don't understand development without understanding evolution. They're completely intertwined. So evolution constrains biological development, but ontogenesis constrains how things are allowed to evolve. So in terms of machine learning evolutionists as a paradigm, we've basically taken it to the max, because basically we've added all the evolutionary mechanisms that just weren't known 20, 30, 40 years ago. So really we kind of complete the paradigm of the evolutionists using results that we talked about earlier. The second tribe, he doesn't include it, he mentions reinforcement learners, reinforcement learning. But it is a tribe in its own right, because Demesis Habas of DeepMind, okay, obviously a very important company and a big clan within a tribe, has expressed again in his writings and his lectures the idea that reinforcement learning is key to what DeepMind does. Okay, so basically we've shown earlier on basically how we can completely do reinforcement learning by reverse engineering the brain, by going into dopamine systems and how these kind of striatal loops actually work based on neurophysiological evidence. Okay, when it comes to connectionists, okay, if Geoffrey Hinton says we need to do away with existing neural networks and start again, what do we start with? How about we basically formulate neural networks that work like how the brain works? And then with respect to the symbolists, okay, this is back to Noam Chomsky. Okay, basically we have the same language to describe binary tree language, to describe language, and it's the same for neurons, the same for reinforcement learning loops, and for the process of ontogenesis. This theory basically explains that language is exactly Noam Chomsky's kind of recursive generative process that generates an infinite array of structured expressions. So basically what we're saying is basically there's a way of looking at the evolutionary machine learning paradigm, reinforcement learning, connectionism, and also symbolists that see it as really one unified theory, one unified algorithm, and that algorithm is DSA, differentiate, select, amplify, intersecting with a backward chain. Okay, So basically, this is where machine learning meets our most fundamental idea in artificial intelligence. Now, okay, what about the analogizers? Strictly speaking, 5 and 6 analogizers and Bayesians aren't strictly speaking a separate tribe, because in a sense, all of these earlier tribes do analogizing. Okay, so analogizing, basically the idea that you can't have brittle analogies. So we solved the analogizing thing with our flexible representations we saw earlier. Okay, so basically literally have a flexible recursive language, hierarchical flexible language that allows us to deeply analogize. As for the Bayesians, okay, there's one formula in this talk. So it's one mathematical formula. It's utterly simple. Okay, the Bayesian formula, of which basically it's a very big idea in statistical machine learning. The Bayesian formula is so easy, you could have derived it by accident in high school. Okay, with what you learned in high school, you could have been looking out the window and basically derived the Bayes formula by accident. Now, the Bayes formula, the ramifications are quite big, and a lot of it isn't relevant for understanding the brain. A lot of it's relevant for statistics, and basically you get like textbooks that thick on Bayesian analysis. But that's the Bayesian formula, and it's utterly simple. Now, what's the significance of the Bayesian formula? Okay, this is the one equation in the talk. Okay, basically it's probability of A given B. Now, how we fit it into our unified theory is basically what we're interested in. Of course, we're interested in A given B. We're interested in, okay, things happen forwards in time. Okay, we're trying to predict the world because we want the A's given B's that lead to reward. Okay, as a baby, we don't know what predicts reward. So we need to basically extract the B's that predict the A's, predict the rewards. How do we do that? Now, we don't know what the B's are. So basically, there's an infinite number of permutations and combinations of things that might happen that might predict the reward. Okay, so that's an intractable problem, but it's far easier to work backwards. It's far easier to work from B given A. So basically, Bayesian probability used to be called inverse probability. Now, the fundamental inversion is basically you're trying to find A given B in terms of B given A. That's the essential aspect of the Bayesian formula. So basically, we're going forwards in time. The fundamental inversion is backwards in time. Now, okay, why is B given A far more of a tractable problem? Because once we experience the reward, it's far easier to basically look around and see what happened in a few seconds before the reward was attained. Do you see? Once we have, we're trying to find A given B, but it's far easier to register the B's given A. Already we've got the reward. There's a tiny subset of things that happen before the reward is registered compared to all the things that can possibly register a reward. So it's far easier to work from once we kind of like B given A and backward chain from the rewards. And once we have kind of B given A, then basically we make that B sticky. So then we can backward chain the fundamental inversion. Okay, it's time inversion. We backward chain backwards in time. It's a far easier problem to solve. So this is exactly our backward chain from primary condition reinforcers, or primary kind of like primary unconditioned reinforcers to make condition reinforcers. So this is how we basically integrate basically the 6 tribes of machine learning with the most fundamental idea in AI. So basically, what we have, this unified theory of genomics with the brain, basically allows us to unify existing AI, but also it does it in a way which takes these existing paradigms, it basically extends them, it basically solves problems and shows the essential symmetry underlying these separate machine learning techniques. So basically, it's a unified theory of existing AI and machine learning. By using these ideas from biology, we basically take evolutionary learning to the max, reinforcement learning to the max, and we have neurons, artificial neurons based on how real neurons work. And basically an idea of language based on Noam Chomsky's work as a generative process. Okay, now what's missing in artificial intelligence? Okay, what is the biggest names? What they say is the next step. Okay, what they say is the next step. These ideas come again and again. It's the idea of generative AI. Geoffrey Hinton, the idea in lecture 2013, says the next step is generative models, generative AI. Judah Pearl, okay, the idea of causal AI is the next step. Jan LeCun, a big name in deep learning, okay, predictive models, predictive AI is the next step. Now, predictive AI, causal AI, generative AI, they're not mutually exclusive ideas. Now, if I generate patterns forward in time, then I'm predicting. Now, if the patterns I'm generating forwards in time match up to patterns in external reality, then there's a possibility I'm extracting the causal relationships in external reality. So you see, generative AI, causal AI, predictive AI, they're actually interrelated concepts. Now, what this theory describes, this unified differentiate, select, amplify algorithm, is a way of doing artificial intelligence and understanding the brain and genome that sees it as one great big generative predictive causal algorithm. Okay, so this is the next step according to the experts. Now, okay, there's something missing. Okay, there's something missing in current AI. It's a big, huge problem. We're going to solve it. We're going to show how to solve it now. Okay, it's a missing thing. And it's basically our diagram earlier. It's called recursive self-modification. It's a huge problem. Okay, recursive self-modification. The technological singularity is recursive self-modification happening on a planetary scale. So the entire world, industrial, scientific, technological complex, basically recursively self-modifying itself with kind of human-level artificial intelligence. Now the trick is, how do you create recursively self-modifying AI? It's a problem. It's way beyond current machine learning and artificial intelligence, which basically ideas from 40, 50 years ago. You know, recursive self-modification is like, it's like sex in an undergraduate computer science class. Okay, everyone talks about it, everyone knows it's really important, but no one knows how to do it. I mean, and that wasn't a joke, by the way, that was a personal observation. No, I'm kidding, I'm joking. Well, anyway, like, recursive self-modification is a really hard nut to crack. Okay, basically, how do we do it? How can we possibly do it? The answer is basically we do it using our discrete mathematical binary tree language. Okay, let me explain what is a mapping, what is a function. So what we want to do is we want to explain the idea of a generative mapping that can generate these differentiate, select, amplify kind of structures, basically. So, okay, what is a function and what is a mapping? Okay, so basic maths, okay, so basically that's a function, but the very kind of like, the kind of like theoretical maths, how you basically understand it on a most fundamental level is to see a function as a mapping, basically. It's called a Cartesian set, and we won't have to go into those kind of details, but basically you have a domain and you have a range. So basically the domain might be X, and that the range is then Y, so X maps to Y. So you have a mapping, so you have a function. So basically any function in maths can be represented as a mapping. Okay, so now what is a generative mapping? Okay, so mapping is a really kind of universal concept. So basically, we talked about functions, logical implication, conditional probability, these are all mappings. Now, importantly, a neuron or a gene, okay, the dendrites, a certain combination, okay, maps to an output. So the operation of a neuron, a gene, a kind of patch of cortex, a cerebral cortical column, they are mappings. So it's a really universal concept. Basically, one pattern maps to another pattern. I recognize this side of the domain, then I reconstruct a pattern, I map to that pattern. So this universal concept can be visualized using what we had earlier. So basically, the formation, okay, just to make it easy to visualize and understand. Now, what we had earlier, the formation of a arm hand, one bone, two bones, many bones, digits. Okay, that is a generative mapping. So each of these steps is a mapping. That's mapping to that, and then you can map that to that, etc. So that's a mapping. That's a and recursively apply the generative mapping to generate one bone, two bone, many bones, digits. So that's a generative mapping. You can apply this idea to anything. You can apply this idea to any binary tree. Okay. Now, how do you explain recursive self-modification? Okay, what's he done here? Oh no, what's he done here? Okay, domain and range, but look, we're recursively self-modifying, so the functions have to be also parameters. The operators have to be operands. So basically, there's no domain, there's no range. So basically, look, the mappings are in this kind of object, stimulus response. I sense one thing, then I map it to another thing. So the arrow is mapping. But instead of having a domain and range, basically it's recursively self-modifying. So these things recursively self-modify themselves to extend the number of stimulus response mappings. Okay, that's a really abstract concept, isn't it? And okay, so the idea of a process can create structure, then the structure also then carries out that process. So the structure is a neuron or a gene, which is a structure, a physical thing, but it carries out a mapping, a process. But then the idea of recursive self-modification is the notion that basically these structures enact a process, but the process also creates more structures. Okay, that's really abstract. Let's go back to our kind of generative mappings, creating digits and arms. Okay, to just make it concrete, because it's kind of abstract to understand, isn't it? Recursive self-modification in this context means that basically the output from previous stages becomes the input for later stages. It's a very old idea that evolution evolves evolvability. It's been around for decades. That evolution is a recursively self-modifying process. You don't understand evolution without understanding the idea that evolution evolves evolvability. Now, one example of this, the easiest way to understand recursive self-modification in this context, is the notion that, okay, a centipede, okay, has 100 legs. Well, it doesn't. It has less than 100 legs, about 20 or 30. Okay, but okay, a centipede doesn't have to re-evolve the legs 100 times or 20 times or 30 times. Okay, once it's got a basic blueprint for one leg, it just duplicates that one leg. Now, what we have here, you don't actually have to re-evolve the finger. Like, okay, I've got 5 fingers or 4 fingers, 4 fingers and a thumb. I don't have to re-evolve the finger another 3 times. I basically use that same building block to make a hand. And once I have an arm and a hand, a right arm and right hand, I don't have to re-evolve from scratch a left arm and a left hand. I basically take a mirror image of that and I apply it to the other side. What it means is that the output from previous stages becomes the extensions for future outputs of the algorithm. And this is called chunking. And some cognitive scientists think that chunking is the key to understanding learning and cognition itself. But it's recursively self-modifying. And what we consider for arms and digit formation can also apply to DNA, to genes, to neurons, to ideas, because you have this universal language that spans all of it. So this is one easy way to understand recursive self-modification. The other thing, which is a bit harder to kind of visualize, is basically if we have a sensing end and a doing end, and effectively this is the doing end, what gets reconstructed. The sensing end is the context sensitivity, which also evolves. So this is basically, once you have the two together, then basically you have these kind of recursively self-modifying mappings that fully bring about recursive self-modification, but it happens starting from the bit level upwards. Okay, so we're going to go into some more fundamental ideas now. Okay, so we're about to come to the end of the talk, so it's a really long talk, but I mean, this is the kind of the big ideas now going to be introduced now at the end. Okay, if we have this notion that basically progenitor fields are binary. Okay, so basically progenitor fields become 2 progenitor fields in a binary bifurcating way. Now, if we backtrack the process of kind of digit formation, backtrack, then where do we begin? We begin from the primary first progenitor field division. So fertilized egg becomes a blob of homogeneous cells, and the first division is basically the first subdividing into 2 different progenitor fields. It's a binary branch. This gives the answer to a key question in biology and evolutionary theory, which is what is behind the mystery of the Cambrian explosion. The Cambrian explosion is basically, for a long time, life on Earth was basically single-cellular animals, basically single cells. And these might be clustered into big groups. And some of these animals are basically like homogeneous blob of cells, basically. But then suddenly, this Cambrian explosion, biological complexity arose, complex forms suddenly arose. What happened? Well, the simple answer is, if you understand that ontogenesis development is a bifurcating diagram, you need to evolve the mechanisms to bifurcate progenitor fields. So we basically have all these mechanisms in this diagram of morphogen epicenters and signaling elements and basically all these components in this diagram. You have it in a single gene battery that I can use again and again in a recursively self-modifying way. You have the rudiments for basically creating the bifurcation diagram, which basically explains all complex animal forms. It sounds awfully like a Hox gene, actually. It basically means that this way of looking at things starting from a simple binary branch allows us to explain how the process of complex biological form arises in the first place and why the Cambrian explosion happened. This leads to even deeper ideas. Okay, we explained the Cambrian explosion. This leads to some really deep ideas. We kind of talked briefly about Chomsky earlier on. Chomsky's quest for actually we talked about Chomsky in the questions and answers. It probably won't be in the video edit. So let's go through that again. Chomsky basically spent his life looking for universal grammar. Okay, so he spent his life looking. He hasn't found it yet. Universal grammar is the ultimate distillation of all human language. Now he thinks there is a strong minimalist thesis, the ultimate atomized, the furthest you can take universal grammar, the ultimate distillation of all human language. He asks, what is the nature of that recursive generative process that gives rise to an infinite array of structured expressions that is all human language? We propose that basically once you understand that basically everything can be encoded in this binary language. Now Chomsky himself says that the strong minimalist thesis might reduce the pair merge, which is a binary tree. So pair merge is a binary branching of two things merged together. When you have this basic mechanism starting from one bit with a single branching, then basically recursively self-modifying, that is the answer to Chomsky's universal grammar and the strongest possible minimalist thesis. There's another deep kind of question in mathematics. Okay, we discussed earlier how Bertrand Russell and Alfred North Whitehead reduce all mathematics to set theory and discrete mathematics. Okay, it goes even further because all discrete mathematics reduces to what's called formal axiomatic systems. There's the question of what's the simplest formal axiomatic system? And then there's a question of, is there a dynamic formal axiomatic system that can generate all the other formal axiomatic systems? This is absolutely mathematics at its deepest and most abstract. A 10-page proof written in normal mathematics would take about 100 pages written in set theory. But written in what we're talking about would take 1,000 pages because we're basically walking at the bit level. We're saying basically there's a formal axiomatic system working at the bit level that can generate all the labels, all the patterns, spatial temporal patterns, but can also generate the rules of transformation because it's recursively self-modifying. The operators also operands. Okay, there isn't a sharp demarcation between mathematical language and human language because all mathematical formula and all mathematical language I can say in human language. So there's not a division between mathematical language and human language. The big idea I'm proposing here is basically when you take things to the minimum, the most minimal, strongest minimalist thesis and most minimal formal axiomatic system, it converges to the same answer. And that same answer is also the distillation of this entire brain, mind, genome ontogenesis theory. It's the same thing. And it's recursively self-modifying. And the question of the most minimal seed AI from which you can create the technological singularity, which is recursive self-modification happening on a planetary scale, involving the entire planetary, industrial, scientific, technological complex. Basically, that's the technological singularity. What this theory gives an answer, basically, recursive self-modification starts from one bit and a single binary branch. So all these separate questions of Cambrian explosion, the most minimal seed that you can create AI and technological singularity from, the most minimal formal axiomatic system and the strongest minimalist thesis, there is a single answer which unifies all of them. It's the same answer. Now it sounds awfully like monad, doesn't it? It sounds awfully like universal and perfect language. That's another talk altogether. Okay, so basically, recursive self-modification of bits and most simple possible binary tree gives rise to everything we talked about earlier. The symmetry between life and intelligence as we understand it. And it's also the key to understanding what is the nature of life and intelligence. Okay, so this is to end the talk, this is really the conclusion. What is life intelligence? We're going to explain it. What is the nature of life intelligence? Okay, so this is the explanation. This diagram basically is all physics. You probably can't see it. General relativity, quantum mechanics, all the kind of mathematics behind it. And right at the bottom is discrete mathematics and formal axiomatic systems, formal systems. What it is basically all physics and all the mathematics underlying physics. Set theory, natural numbers, integers, rational numbers, basically fundamentals, kind of bedrock of mathematics. And right at the bottom you have what we talked about earlier, set theory, discrete mathematics. But right at the bottom, at its most abstract, is formal axiomatic systems. Now, there's an idea that basically beautiful mathematics corresponds to some things in physical reality. So here, general relativity was based on non-Euclidean geometry. Now, non-Euclidean geometry was studied separate from physics for its own mathematical beauty and intrinsic logical consistency. And Einstein came along and applied non-Euclidean geometry, and perfect match to the nature of space and time. So a notion that beautiful mathematics corresponds to physical reality. Now, if there's this exquisite mechanism happening at the deepest level of mathematics, at the level of discrete mathematics and formal axiomatic systems called recursive self-modification, that's also the distillation of this way of looking at life and intelligence and genomes and ontogenesis and evolution. Okay, basically, if there's this exquisite mechanism happening at the deepest level of mathematics, then to what does that correspond to in the universe? Well, obviously, the answer is life and intelligence. So therefore, the answer to what is the nature of life and intelligence, it is the physical manifestation of, in the physical universe, of this recursively self-modifying process happening at the deepest level of mathematics. And that is how fundamental life and intelligence are. And that's what you need to create. That's what you need to, this recursively self-modifying loop, that's what you need to create true recursively self-modifying artificial intelligence. Okay, there's more. So this diagram basically it shows the unification of genomics, ontogenesis, and evolution, and neuroscience and cognitive psychology, and linguistics and universal grammar and the strongest minimalist thesis, discrete mass and formal axiomatic systems. And here, computer science and AI. So that's all unified in a unified theory. Now, another talk and is the notion that everything we talked about tonight extrapolates to the universe, which is the answer during the break. The question and answer during the break. So basically, this section here is basically probably the next talk, the extrapolation of everything we talked about into the universe. Okay, so basically the Upanishads, as is the human body, so is the cosmic body, as is the human mind, so is the cosmic mind, as is the microcosm, so is the macrocosm, and as is the atom, so is the universe. These ideas of life and intelligence as a single recursively self-modifying process happening at the bit level, simple binary branch level, extrapolating the universe, is the full manifestation and the fulfilling of that line from the Upanishads, a Hindu holy text for the 21st century. And it also gives rise, also leads to the explanation for consciousness, which I don't have time to, it's a bit involved, but ask me in questions and answers at the end. Basically leads to a fractal universe, fractal brain, leads to the answer to nature of consciousness, which I'll do in the next talk. But anyway, okay, so we've covered a lot of ground, haven't we? So just to finish off, I mean, okay, so we started with a Great Britain called Stephen Hawking, the invention of artificial intelligence be the biggest event in human history. Now, William Blake has been called England's only prophet. Okay, he's uber mystic, a real interesting guy, and a great poet and engraver. Now, like many people during his time, he believed that the great historical happening would happen in London and England. Okay, that's what he believed. It would happen in England's green and pleasant land. Jerusalem's not about the past, it's about the future. Because he also wrote in another less known poem, he also wrote that the fields from Islington to Marylebone, Primrose Hill to St. John's Wood, were builded over with pillars of gold, and there Jerusalem's pillars stood. He's talking about the future. So he thought the great historical happening would happen in England and London. If Stephen Hawking says AI is the biggest event in human history, maybe they're talking about the same thing. Okay, I know this is a bit far out. I believe that basically the creation of AI and the launching of the technological singularity is going to happen in London and along the M4 tech corridor, including Bristol. Okay. So include the audience in the talk. Always do that. So basically, we believe that basically the great historical happening that William Blake was talking about, he's a prophet, and I really do believe that, basically, that we can actually, in Brexit Britain, basically, that the great happening will happen in this kind of like, London is the Vienna of the 21st century. Empire declined. It's kind of really creative place. That would happen in London, southern England, Bristol, M4 corridor, Oxford, Cambridge, etc. All the places that voted Remain. Okay, so that's what we believe. So William Blake's prophecy is going to come true. The biggest event in human history is going to happen in London, Bristol M4 corridor, the founding of the startup at the end of time. Because creation of AI is not just the biggest event in human history, it's more fundamental to that. It is a fundamental phase shift in the entire historic evolutionary progression on the planet. It is as fundamental as the Cambrian explosion. It is as fundamental as the emergence of civilization and humankind itself. So, and we believe this epicenter is really, where we are, and it will happen in your lifetimes in a fairly short space of time, I believe. So, technological singularity, startup at the end of time, coming soon to a planet near you. Okay, thanks very much. Oh, great. That's